In this video, we are going to go over a couple huge ideas. This is your video notes. We're going to call this conservative forces. All right. Now, with this topic, we will be doing some calculus. We're going to be doing some integrals and some derivatives, so you can see how all this ties in together. All right. So let's begin. The first thing I want to do is I'm going to actually type this out because there's a lot of things to write. Let's go with the couple of known facts. All right. So first, all conservative forces have a U, aka potential energy association. Okay. So far we've come across UG, which is gravitational potential, and we have US, which is spring potential. So both of those forces are what we call conservative forces. All right. So what do conservative forces do? We'll get into that definition a tiny little bit, but just to go forward with a little bit more of the definition, all conservative forces are what we call path independent. Okay, so which means the path or the way the I guess object slash system travels does not matter. Okay, so it doesn't care about the motion part of the object that is traveling. So let me give you two examples of this. The first example, we have a object here, okay, and the object is on the ground, so height of 0, and we raise the object up here to a new height, and we call this height h, okay, or hf, or final height. Now, in the same kind of scenario, what if instead of lifting the object straight up, we took the object here, okay, and we took it on a really wild ride, right? We go here, we spin it around, we go up, we go down, and we go all over the place. But the important thing is that at the end of this journey, we end up at the same HF. Okay, so in this case, we can say that the final potential energy, so our UG, is still equal to mgh. And our UG here is also equal to mgh because that height doesn't care about the path that it travels. So that's path independent. So the amount of work that the Earth did only cares about this vertical path. And so you might be thinking, well, what about the, everything that's in between, okay, which is like this part here? What about all this? So the thing about this part is if we're to think about the box, okay, so if we were to lift the box up and then let it fall down and let it go up again. All right, so let's say we do a up, let it fall down, and then up and back in. So when we go up here, we're doing work on the box to let it go up. Okay, so potential energy is gained. But when it falls back down here, potential energy is lost. And when we go back up here, potential energy is gained again. And so when we take a look at this middle portion, all right, so the path, the reason why the path doesn't matter, except for the start and the end, is because whenever you go up, you go down, you go up, you go down, right? So there's an added energy, there's energy that is taken away. And so the sum of all the work done, or the sum of the potential energy gained, will even itself out or cancel itself out mathematically. And so the only thing that matters is your starting point and your ending point. It is path independent. So a very popular question that you might see here is, let's say we have a ball that is at this height h here, okay? And let's have three different paths. So we'll have path A, okay, and we'll have path B, and we will have path C. And path C, I'm going to try my best to make it as steep as possible, like this. All right, so we have path A, B, and C. And the question is, which object will have the greatest kinetic energy, aka the greatest velocity at the end, right? And they both end right there at the end. So in order to answer this question, remember the path itself doesn't matter, only the starting point and the ending point. And if we know that your starting height, your h initial is h, and your final height, hf, is 0, we can say that starting off, they all have the same potential energy. And that potential energy at the end will be the same kinetic energy. Okay, so both objects will reach the final position with the same velocity. So we can say VA is equal to VB, which is equal to VC. All right. The other thing that we can think about is, so this might be question part one. Question part two is which object will reach the end first? Now, when it's asking about time, okay, time, remember, is all about the kinematics unit. If you remember, none of the energy formulas actually use time. And so we can't use the same idea here using the conservation of energy to answer that question of which object will reach the bottom first. By the way, the answer is object C, and that's because it has the greatest acceleration in the beginning. So it'll speed up the most. So if it speeds up the most, it'll have the distance that it travels will be covered in a quicker amount of time. Okay, so C will reach the bottom first, and I think A will probably reach the position last because it has most of the flat parts here, so it's not accelerating as much in the beginning. All right, okay. So that's what it means by being path independent. The path for energy does not matter. Okay, so it's just your starting position and your end. Everything in between does not matter. All right, so let's go back to the definition of the conservative forces. So one of the things about conservative forces is that one of the big definitions, it makes the object go towards the lowest potential. So we could think about this with a couple of real-life examples. So the two conservative forces that we just discussed was gravitational potential and spring potential. So with gravitational potential, if you have an object at a height h up here, okay, thanks to the force of gravity, the gravitational force will have that object go to a lower height. So in this case, a height of 0. Okay, so all conservative forces will make sure the forces go to a lower potential. It's just the nature of the universe. Now, this idea here is key, and it'll pop up when we take a look at the formula. So what about the spring? Well, so if we have a spring, okay, and we attach a block to it, if you stretch the spring down, like so, you extend the spring here, which we call delta x, the object will have to go back up. It'll spring back up, and eventually it wants to go back towards its original position. Okay. Now, if you squish the object up here and you scrunch it, okay, and you release it, the spring will bounce back and forth. It'll go up down, up down, up down, but eventually it'll reach its original equilibrium point right here. Okay. So even the spring wants to go back to a equilibrium position. So the main idea of conservative forces, it wants to go back to its lowest potential. For MGH, the lowest potential is based on the height. Okay, and for a spring, which is 1/2 kx squared, the lowest potential is when x is equal to 0, or how we say no compression, okay, or an equilibrium point. All right. Now, on the flip side with this, the important thing to know here is when the object is at the lowest potential, okay, the way that the conservation of energy works, lowest potential means most of the time greatest velocity. Because if your potential energy is down, that means your kinetic energy is up. And so we can see that here, right? When we drop an object from a high height to a low height, the greatest kinetic energy is at the bottom, and for a spring, okay, when we release it, the greatest potential kinetic energy will be here at this equilibrium point. Because when it's fully stretched, our kinetic energy here is 0, or when it's fully scrunched, our kinetic energy is 0. It's not moving. Cool. All right. So with that being said, let's come out with the formula. So we say the potential energy is a function of position. So let's start off with that statement. So U of x, okay? All right, so there's a couple of things that we're gonna look at to help come up with the formula for this potential energy. All right. So the first thing is we're going to start off with the work formula. Work is equal to force times the displacement, okay, or delta x. So I'm going to rewrite this as F dx, okay, because that delta just simply means a change in x. Now, work. Work is what we call a change of energy. So I'm going to put that off on the side. Work is change in energy. And if we know that we have a change in energy, we can just rewrite this as dE. Okay, much like how delta x is dx, delta E is just dE. But because we're looking at potential energy specifically, we're going to rewrite this as du. Okay, so we're not looking at just any kind of energy, but potential energy in specific. Now, we need to represent the idea that potential always goes from high to low. Okay, so if potential energy goes from high to low, we represent that mathematically with a negative sign. So that negative will go in front of the negative du. So I'm going to do a substitution for work, right? We derive that here, and we just substitute that in right there. And let's just put that here as a little note. The negative symbol, okay, represents so what we like to call the nature of the universe. Okay, nature of the universe always wants to go from high potential to low potential. All right, and that's what that negative symbol represents. Okay, all right. So with this formula, if we were to rearrange that formula, we can also get that force is equal to negative du dx. So what this shows us here, right, and this is important, is that if given a ux function, okay, the derivative gives us the force. Okay, now to be specific, the force here is the conservative force. Remember, all the conservative forces makes the potential go from high to low, and that is just the nature of the universe there. We found how to take the derivative of a potential function with respect to position. Let me show you the other formula that you can use when we're dealing with the work energy stuff. All right. So the first thing that we have to realize, we got to go back to the conservation of energy. So the conservation of energy states that the change in your kinetic energy has to equal to, before that, the change in kinetic energy plus the change in potential energy of any kind has to equal zero, right? So one form of the energy plus the other form, right? Because there is no difference between them, right? Because the energy before and the energy after, they have to equal to each other. So if we rearrange this, we get delta Ke is equal to negative delta U. And so we're going to be using this right here in order to help us define the formula for work energy. Now on the formula sheet, you'll see the formula for work to be W is equal to the integral of force times the dx. Okay, where this shows us, so that integral shows us right here. This means that we are path independent. Okay, so I guess what you could think about is here, this is your initial position, and here, this will be your final position. And so what it means by path independent is it doesn't care about how you go from your initial to your final. That integral takes that into account. All right. Now, from this equation, we can come up with two other forms of the equation because we know that work is equal to the change in energy. So if the problem is looking for, like if you're doing work on a block, so for example, if you have a block and you exert a force on it, right, at the end of the push, it's going to be moving. So this is a change in kinetic energy. So if you have a change in kinetic energy formula, you have delta Ke is equal to the integral of f dot dx. However, if you are looking for a block that goes from point A to an elevated point B, okay, we got to use the change in potential energy formula. So that'll be negative delta U is equal to the integral of f dot dx. Okay. Now, this could also be applied to the spring potential energy formula, but yeah, here we go. Those are the two integrals that you can use in alongside of the derivative form. Okay, so you want to be using the integral if the problem gives you the force. Okay, if it gives you a force function, compared to up here, you want to be using the derivative form if the problem gives you a potential function. Anyways, that's it. We'll get more practice in the next video. We're going to go over the energy graphs, and yeah, that's gonna be a doozy. Until then, see you next time. Bye bye.